Nice to meet you in an online meeting. I'm Liu Junwei. Today I would like to talk to you about some of our work in the field of flash memory. My research title is ApproxRefresh, enabling uncurrentable data reuse on flash memory with approximate read awareness. With the increased density and technology scaling, flash memory is more vulnerable to noise effects, overwhelmingly lowering the data retention time. The periodic data refresh technique is commonly used to retain the long-term data integrity. However, the frequent refresh requests also introduce the increased access conflicts and several write amplification, leading to suboptimal performance and lifetime improvement. Therefore, in this work, we are aiming to reduce the flash refresh costs to improve flash memory performance. We found that uncurrentable data rates considerably with the increased refresh frequency in SSDs, and the approximate computing application has the inherent error tolerance. This provides a great opportunity for us to explore them for improving refresh performance. So we propose the approximate aware refresh scheme, ApproxRefresh, which enables uncurrentable data reuse with the existence of approximate computing applications. We will also show that ApproxRefresh reduces the refresh latency greatly over the state-of-the-art. First, let me introduce some background and motivation in order to understand the details explored below. Because of the physical characteristics of the floating gate transistors, FGT, the number of charges stored in FGT may change abnormally in program, causing data errors. We showed four main error categories. So for correcting row bit errors, error correction code ECC such as BCH code and LDPC code is being used in SSDs. But when the number of bit error exceeds the error correction capability of ECC will fail to recover the original date. So how to deal with it? Besides ECC, periodic data refresh technique is also one common solution to deal with the deteriorated data reliability program, which periodically reads the data out, currents possible errors, and then remaps the data into new locations. However, the extra operations may affect health performance and longevity, so our goal is to reduce the refresh costs. Now, let me introduce some background about approximate computing used in our scheme. Approximate computing explores the error resilience of the approximate data. With the support of approximate computing idea, we could explore precise read and approximate read for the same data. In contrast to prior works, our work first explores the uncurrentable data reuse for reducing the refresh costs. Let's move on the uncurrentable data. It represents data within the specific time interval between the end time of the refresh operation and the start time of the next eraser operation. This figure shows the total quantity of the uncurrentable data increases dramatically with the refresh intervals decreasing from 3 days to 1 day and then to 1 hour. Our experiments observed that the uncountable date rises and exists for a long time because the row beta error loads RBRs of the flashy pages increase and SSDs are more vulnerable to errors. So how can we fully utilize the uncountable date? Second, here give our ApproxRefresh mechanism. It had two key ideas. AR-RFR selectively adopt RFR or RBR to reduce the refresh costs and the read disturbance. Then ApproxGC is proposed to fully utilize AR-RFR. This figure shows the overview of ApproxRefresh. The high level includes error resilient applications and traditional applications, which transfer I/O requests to SSDs. And at the low level, we also implemented some special commands for handling the read requests accessing the uncountable date page. The device level would be highlighted now. Okay, we are going to take a look at the RFR. RFR is designed to enable and exploit the uncountable date reuse in the refresh scheme. The basic idea of RFR is to maintain the long-term data integrity by only remapping an enhanced ECC. Then, the subsequent approximate operations can be directly scheduled to the uncountable date page without any read performance loss. This figure illustrates the clear procedure of RFR. In the first and second steps, all the valid pages in the vector block are read out and corrected by the default ECC engineer. Then, in the third step, RFR computes an enhanced ECC with more parity bits for each page, which can count more errors. So, what is enhanced ECC? Now I would like to introduce it clearly. The enhanced ECC adapts more parity bits to enhance the error correction capability of ECC. The number of parity bits for the enhanced ECC is calculated according to two models: error correction strength model and flash reliability model. Besides, on the above models, we can obtain the estimated maximum bit error loads. Then the new code would length for the enhanced ECC would be generated. In the first step, we need to match new ECC parity bits for multiply uncountable date pages into one ECC page. This figure shows the difference of normal flash page and our designed ECC page stored in dedicated ECC block. To consider the index of locating the exact position of each parity entry, we use the specific metadata to sequentially locate the corresponding LPN of each parity entry and associate them with the original user date. To prevent one parity entry storing in more than one ECC page, we directly for the unused end part of the data error with 1. In the fourth and sixth steps, we expose sets of read or write interface to access flash memory as table shows. Okay, we have learned about the AR-RFR strategy in the above introduction, although it reduces the refresh cost dramatically, it also inevitably increases the process rate latency. So we propose a level approximate rate aware AR-RFR mechanism. The main idea is to decide a proper refresh model based on the approx rate and process rate hotlist of vector pages. Research often uses the times of read requests to identify read hotlists, so we set two different thresholds, TR-read and TP-read, to identify approx rate and process rate requests historical hotlists. Then we categorize the valid pages in the vector block into the four types: AP underscore hot, P underscore code, A underscore code, and AP underscore code. With the hotness type information, we can design the ways to choose the best refresh mode. As the algorithm elaborates, for AP underscore code and P underscore code pages, AR-RFR tracks RFR because these data pages are rarely process rate by applications, and once one page becomes to be frequently process rate, which would be optimized for A underscore code and AP underscore hot pages. AR-RFR tracks RBR. So by AR-RFR, the rate counts on the process pages are significantly reduced. Next, let's move on to the flash translation layer design. To locate the ECC page and the original uncurrentable data page, the page mapping table needs to be revised. We add one ECC mapping table, EMT, and one uncurrentable mapping table, UMT. Then, because the traditional Grandy garbage collection would reclaim the block with the most number of invalid pages, regardless of their page types, we enhance the Grandy garbage collection. We merely consider the vector block selection and the process rate hot code separation. Okay, now let's move on to the experiment and analysis. We evaluated the ApproxRefresh enabled SSD implemented on the chance-driven simulation platform SSD Sim. The detailed SSD parameters are shown in Table 2. In the experiment, we implemented and compared the following four schemes. So, first, we compare them with the refresh performance. We can say ApproxRefresh achieves a significant overall refresh latency reduction. Second, we compare them with I/O performance. We can say ApproxRefresh achieves great read and write response time reduction compared to FCR. The I/O performance improvement mainly comes from the improved refresh efficiency. Okay, as a conclusion, we have designed ApproxRefresh to enable uncurrentable data reuse with the assistance of approximate computing applications. ApproxRefresh selectively adopts the remapping-free refresh or remapping-based refresh with the approximate rate hotlist awareness. A corresponding ApproxRefresh garbage collection algorithm is also proposed to fully utilize ApproxRefresh. Experimental results show that ApproxRefresh reduces the refresh latency greatly over the conventional remapping-based refresh technique. That's all for my presentation. Thanks for your attention. If there is any question, please email me.